In today's lecture, we are going to learn some more tests about convergence of an infinite series. One is called the ratio test, the other is the root test. Both has wide applications in testing whether an infinite series converges or not. And then we are going to deal with series which are not necessarily of non-negative terms. We are going to deal with a particular kind of series called alternating series and try to understand the notion of convergence for that kind of a series. So first we start with ratio test. The ratio test actually is an outcome of the comparison test. We will see how it is related to the comparison test as follows. That suppose I have ANs which has the following property, that modulus of AN plus 1 by AN is less or equals to Q, where first of all this quotient should make sense. So I will say AN not equal to 0, and I put a condition 0 strictly less Q strictly less 1. Okay. And I assume that this inequality is true eventually. That is, after one stage, this AN plus 1 by AN is less or equals to Q. So in particular, what I mean is that mod AN plus 1 divided by AN is less or equal to Q, let us say for all n bigger than or equal to some capital N. Okay. If this happens, then summation AN converges absolutely. Okay. This is part A. Then the part B is if modulus AN plus 1 by AN strictly bigger than 1 for all n bigger than or equals to capital N, then summation AN diverges. Okay. So let us see once again, what did I say? That suppose I have an infinite series summation AN. I want to test whether it converges or not. Suppose all the ANs are non-zero, that means all the terms are non-zero. Then I look at modulus of AN plus 1 by AN. If it happens that these quantities are bounded by some positive quantity which is strictly less than 1 eventually, that means after some stage, then the series converges. And if it happens that modulus of AN plus 1 by AN, it is strictly bigger than 1 eventually after some stage, then the series diverges. Now coming to the proof of it, it is very easy to prove it. You will see it's just a simple application of the comparison test. The easiest part is to prove B first. The given condition says that mod AN plus 1 is strictly bigger than mod AN if N is bigger than or equals to capital N. In particular, I can say that mod AM is strictly bigger than mod A capital N for all M bigger than or equals to capital N. This simply means that the coefficients ANs of the infinite series, they don't converge to 0. Because if AN converges to 0, then after some stage they have to be less than epsilon for arbitrary choice of epsilon. In other words, they can be made arbitrarily small after some stage. But here we see that it can never be made smaller than modulus of AN because it is always bigger than modulus of AN. That implies that the sequence AN does not converge to 0. This implies summation an does not converge. So B is simple. Now coming to A, what is given to me? It is given that modulus of an plus 1 divided by an, this is less than or equal to q for some q which lies between 0 and 1. This q is a constant, it does not depend on n. This is true for all n bigger than or equals to capital N. Now this then implies that mod an capital N plus 1 is less or equal to q times modulus a capital N. And also modulus a n plus 2, I can look at that, that is less or equal to modulus of a n plus 1 into q, which is further less than or equal to q square into a mod n, mod an. This way I will get finally that mod a n plus r is less or equal to q to the power r times mod an. Okay, this is true for all r strictly bigger than 1. What does this mean? That means the infinite series, if I look at summation an, then for large n, mod an is dominated by a geometric series of the form summation mod an times q to the power r. Because of my assumption that q lies between 0 and 1, this geometric series converges. Okay. Then by comparison test, summation an converges. Okay. So it is just a simple application of the comparison test. But what is fundamental here is that q lies between 0 and 1. Now once we have this, now as a corollary we can have the standard statement of the ratio test, which you can have in many books, and that is in a form which is readily applicable. So that form says that summation an I look at where an is not equal to 0 and limit n going to infinity modulus of an plus 1 divided by an equals to L. Suppose I have this. So I have an infinite series an, all the an's are non-zero, and limit n going to infinity modulus of an plus 1 by an exists and is equals to L. Then if L is less than 1, this implies summation an converges. Number 2 is if L is bigger than 1, then summation an diverges. But what happens if L is equal to 1? If L equals to 1, then the test is inconclusive. That is, the series might converge, it may diverge also. That is easy to see in the following example. So first to illustrate 3. So case 3. Look at the series summation 1 by n. Also look at the series summation 1 by n square. I know that this does not converge. And I know that this converges. What is an here? An equals to 1 by n. And here an equals to 1 by n square. Then what is an plus 1 by an? That is n by n plus 1. Here an plus 1 by an, that is equals to n square. So what is then limit n going to infinity? An plus 1 divided by an. This is same as limit n going to infinity n by n plus 1, that is limit n going to infinity 1 by 1 plus 1 by n, which is equal to 1. And here so we see that in both the cases the required limit of an plus 1 by n turns out to be 1. But in one case the series converges and in one case the series does not converge. That means the case L equals to 1, the test does not reveal any fact about the infinite series. So this test will only apply in the cases when L is less than 1 or when L is bigger than 1. L is less than 1 implies the series converges, that is what is given in 1. And if L is bigger than 1, then the series an diverges. Now let us see a quick proof of this. So we start with 1. Given that limit n going to infinity mod an plus 1 by an equal to L, which is less than 1. I know that. Now choose epsilon bigger than 0 such that L plus epsilon is less than 1 and L minus epsilon bigger than 0. Then by the definition of convergence of a sequence, there exists capital N such that for all n bigger than or equals to capital N, this quantity is less than L plus epsilon and bigger than L minus epsilon. Okay. Now I just concentrate on this part. This is true for all n bigger than or equals to capital N. So according to the previous result which I have proved, this quantity L plus epsilon can be considered as Q. And since by my choice L plus epsilon is less than 1, this Q is less than 1. This implies summation an converges by the previous result. The previous result was if after some stage modulus of an plus 1 by an is less than Q, where Q is less than 1, then the series converges. Here I got exactly the same thing. Instead of Q I got L plus epsilon, but which is less than 1. So this can be considered as Q and hence the previous result applies. Now let's come to the second part. This says that limit n going to infinity modulus of an plus 1 by an is equals to L, which is strictly bigger than 1. What I do is choose epsilon bigger than 0 such that capital L minus epsilon is strictly bigger than 1. Since L is strictly bigger than 1, I can always choose an epsilon such that L minus epsilon is also strictly bigger than 1 and epsilon is positive. Then by the definition of limit, this implies modulus of an plus 1 divided by an is bigger than L minus epsilon for all n bigger than or equals to capital N. Okay. But then I can compare this again with the previous result, that L minus epsilon, as L minus epsilon is strictly bigger than 1, the series diverges. Summation an does not converge. Look at the previous result where I have proved this is the statement I am looking for. See, if n is bigger than or equal to n and modulus of n plus 1 by n is bigger than 1 for all n bigger than or equals to n, then summation an diverges. It does not converge because the terms don't go to 0. That is what is happening. Now, the situation I have at hand is precisely this, that modulus of an plus 1 by an, this is bigger than L minus epsilon, but L minus epsilon is by my choice strictly bigger than 1. Hence the series summation an does not converge because its terms don't go to 0. So that gives you the ratio test. Let us again look back at the statement of ratio test. It says what? That I first have a series summation an. The care has to be taken that all the terms are non-zero. Otherwise, it is difficult to apply the ratio test because you are dividing by something. So if all the terms are non-zero, I look at modulus of an plus 1 by an. And then I look at the limit. Suppose the limit exists, then I have to check whether the limit is less than 1. If it is, then the series converges. If the limit is bigger than 1, then the series diverges. If L equals to 1, then we cannot say anything, we have to try for something else. Okay? Now the next test, what we are going to deal with is called the root test. This is also a consequence of the comparison test, but here the comparison is being made with the geometric series. So for example, suppose the situation is this, that I have summation an, I know that all the an's are bigger than or equal to 0, and let us say 0 lesser equals to an less than or equals to x to the power n, where 0 less x less 1. Okay, then it is very clear from the comparison test that the series summation an converges because the geometric series summation x to the power n converges. This implies if my condition was that 0 lesser equals to an to the power 1 by n lesser equals to x, where 0 less x less 1, then summation an converges. Okay, because an to the power 1 by n lesser equal to x, it would imply that an is lesser equals to x to the power n, and then I can compare. The root test is essentially the same thing written in a different language in terms of the limit. So let me first give you the statement. So I write it as a theorem. Summation an is given, and limit n going to infinity modulus of an whole to the power 1 by n equals to L. Then if L is less than 1, then the series converges. If L bigger than 1, then series does not converge. And the third is like the ratio test. If L equals to 1, the test fails. That is, no conclusion can be drawn. Again, as an illustration of 3, what we do is take an to be equals to 1 by n. Then limit n going to infinity which is certainly equal to 1. But if I start with n equals to 1 by n square, then also this limit is also equals to 1. But summation 1 by n diverges and summation 1 by n square converges. So in this case L equals to 1 and hence the test is not conclusive. So again we just need to prove the case 1 and case 2. Okay. So let us come to the proof. What is given to me? It is given that limit n going to infinity modulus of an to the power 1 by n is equals to L and L is less than 1. Choose epsilon again such that L minus epsilon, L plus epsilon is strictly less than 1. This then would imply that there exists some capital N such that for all n bigger than or equals to capital N, modulus of an to the power 1 by n is less than L plus epsilon. But this would imply that modulus of an is less than L plus epsilon whole to the power n for all n bigger than or equals to capital N. Now notice that L plus epsilon is strictly less than 1. So L plus epsilon to the power n, if I look at the sum, that gives me a geometric series which converges, and modulus of an is less than that. By comparison test then summation an converges. In fact, an converges absolutely. Okay. So in this case we are again comparing and again with the geometric series. Now the second case, that limit n going to infinity modulus of an to the power 1 by n, that is L, and L is bigger than 1. Now choose epsilon bigger than 0 such that L minus epsilon is still bigger than 1. Since L is strictly bigger than 1, I can choose some such epsilon. This implies then, by the definition of limit, that there exists capital N such that for all n bigger than or equals to capital N, modulus of an to the power 1 by n is bigger than L minus epsilon. This implies modulus of an is bigger than L minus epsilon whole to the power n for all n bigger than or equals to capital N. Now notice that L minus epsilon being bigger than 1, L minus epsilon to the power n is always bigger than 1. So this would then imply that modulus of an is bigger than 1 for all n bigger than or equals to capital N. This certainly implies that an does not converge to 0. This implies that summation an does not converge. Okay. So again the statement is very simple. What I do is, an is given, I look at modulus of an to the power 1 by n and I just calculate that limit. If that limit is less than 1, then the infinite series converges. If that limit is bigger than 1, then the infinite series does not converge. But if the limit is equal to 1, then I have to be careful, because in that case the infinite series may converge, it may not converge. Okay. Now let us see some examples here. Let us look at summation. So this is the first example. 1 by log n whole to the power n, n from 2 to infinity. Okay. So here an equals to 1 by log n to the power n. That means an to the power 1 by n, that is 1 by log n. Okay. This goes to 0 as n goes to infinity. So in this case L equals to 0, which is less than 1. Okay. That implies the series converges. Similarly, I can look at summation n by n plus 1 whole to the power n square. So in this case an equals to that means an to the power 1 by n turns out to be which is same as okay. So I can write this as and since we know that limit n going to infinity 1 plus 1 by n whole to the power n is e, which is strictly bigger than 1. This then implies, since I have 1 by, it implies that limit n going to infinity an to the power 1 by n this is 1 by e, which is strictly less than 1. This implies then the series converges. So given an infinite series, now we have certain techniques which we can apply to test whether the series converges or not. The first one, the most effective one, is the comparison test. You try to compare it with geometric series or summation 1 by n to the power p. Then we have the limit comparison test, then we have the ratio test, now we have seen root test. After this I am going to look at series which are not always series of non-negative terms. That means here negative terms can also come, and we want to look at certain tests which will tell me the convergence of this kind of a series. Now we come to something called alternating series. So what is an alternating series? Suppose I have a sequence an and an is bigger than or equal to 0. Then I look at an infinite series of this form, summation n from 1 to infinity minus 1 to the power n plus 1 times an. Okay. Notice then what is the first term of this infinite series? That means when n equals to 1, this is a1. So the series looks like the first term is a1, then I take n to be equals to 2, that means minus 1 to the power 3 times a2, but minus 1 to the power 3 is minus 1, so it is minus a2, then comes plus a3 minus a4 plus a5 and so on. So you see the signs actually alternate from one to the other. First term comes with positive sign, second term comes with negative sign, third term comes with positive sign, fourth term comes with negative sign and so on. That is why the name alternating series. All we are interested in that under which criteria this kind of a series converges. The particular example we have in mind is this series, summation n from 1 to infinity minus 1 to the power n plus 1 times 1 by n. So the series looks like, if I look at first n equals to 1, then the first term is 1, then minus half plus 1/3 minus 1/4 plus 1/5 and so on. Notice that this series is not absolutely convergent, because if I take modulus of the terms, all I get is summation 1 by n, which I know does not converge. But the question still remains, does the series converges? Because absolute convergence implies convergence but not the other way. So we are interested to know whether this particular series converges or not. Okay, that we will get by something called Leibniz test, whose statement is like this. Suppose an is non-negative for all n and the sequence an is decreasing and an converges to 0. So what are the properties? I have a sequence an such that elements are non-negative, it is decreasing and it converges to 0. Then the alternating series, summation n from 1 to infinity minus 1 to the power n plus 1 an converges. Before we go to the proof of this, come back to the example. 1 by n is bigger than or equal to 0. 1 by n plus 1 is less than 1 by n. This is the condition, decreasing, and also 1 by n goes to 0. Hence, by Leibniz test, this would imply that summation n from 1 to infinity minus 1 to the power n plus 1 into 1 by n converges, which is not absolutely convergent. So in particular, it also gives me an example of a series which converges but not absolutely convergent. Okay. So the properties are very simple to remember. For alternating for this Leibniz test, As a model, you should always remember the series minus 1 to the power n plus 1 into 1 by n. The conditions are exactly analogous to this series. That means ans are non-negative, decreasing and goes to 0 as n goes to infinity. Then the alternating series converges. Now let us come to the proof of this. So first we will look at partial sums of the series, but the even partial sums and the odd partial sums. So we want to consider the odd partial sums s2n plus 1 and s2n. Okay, so what are the definitions? Very simple. Usually SM means summation n from 1 to m minus 1 to the power n plus 1 into an. Okay. Now let us see what kind of sequences these partial sums are. Let us first start looking at s2n, whether it is increasing or decreasing or what. So first let's check s2n plus 1 minus s2n. What is this? This is summation I from 1 to 2n plus 2 minus 1 to the power I plus 1 ai minus summation I from 1 to 2n minus 1 to the power I plus 1 ai. Once I write this, many terms cancel except the last two terms. That means what remains is minus 1 to the power 2n plus, that means the term I equals to 2n plus 1. Okay, so it is 2n plus 1, that is 2n plus 2 a 2n plus 1, then the next term plus minus 1 to the power 2n plus 3 a 2n plus 2. Okay, these are the terms which remain. That means what I get is a 2n plus 1 minus a 2n plus 2. Okay. Now I know that the sequence an is decreasing. That property is given to me. That means a 2n plus 2 is less than a 2n plus 1. That means this is bigger than or equal to 0. What does this prove? This implies the sequence S2n is an increasing sequence. Because I have seen that the next term is bigger than the previous term, and that is happening for each n, so the sequence is increasing. Now if I start with the odd subsequence of partial sums, the odd sequence of partial sums S2n plus 1, then I would certainly look at S2n plus 3 minus S2n plus 1. Then a calculation exactly like the previous one tell me that what remains is minus 1 to the power 2n plus 3 a 2n plus 2 plus minus 1 to the power 2n plus 4 a 2n plus 3. That means a 2n plus 3, because minus 1 to the power 2n plus 4 is 1, minus a 2n plus 2. But notice that the sequence is decreasing. That means a to n plus 3 is less than a to n plus 2. So this is less than or equal to 0. So the behavior changes. This implies then that the sequence s to n plus 1 is a decreasing sequence. So the even subsequence is increasing, that is what I got, and the odd subsequence is decreasing. Okay, fine. Now I want to compare between S2n and S2n plus 1. What is the relation among them? So let us look at S2n plus 1 minus S2n. If you write down these quantities, you will see what you get is minus 1 to the power 2n plus 2 a to n plus 1. That is a to n plus 1. Because 2n plus 2 is an even number, so minus 1 to the power 2n plus 2 is anyway 1. So I get that this is bigger than 0 because all the terms are non-negative. So this implies that S2n plus 1 is bigger than or equal to S2n. Now I have two more informations about this S2n and S2n plus 1. I have already seen, so let me write it here, that S2n is increasing and S2n plus 1 is decreasing. Now notice one thing, I can write it in this form, that S2n plus 1, that is bigger than or equal to S2n, I got that. Okay, since it is increasing, it is certainly bigger than or equal to S2, because S2n is increasing, so all the higher terms are bigger than the first term, and the first term is x2, so S2n is bigger than or equal to S2. On the other hand, if I look at S2n plus 1, that is decreasing, that means all the terms are less than or equal to the first term. So that means this is less than or equal to the first term, which is S1, and this is true for all n. This implies then that S2n is a bounded increasing sequence. Similarly, S2n plus 1 is a bounded decreasing sequence. But we know that every bounded increasing sequence or every bounded decreasing sequence, they converge to some numbers. Using that, this implies that S2n converges to some number s, and S2n plus 1 that converges to some number s prime, let us say, because these are bounded increasing and decreasing sequences. Now this implies now that if I look at s prime minus s, that is limit n S2n plus 1 minus limit n S2n, which is same as limit n S2n plus 1 minus S2n, that is limit n a to n plus 1. Now there is another condition on the ANs, that as n goes to infinity, AN goes to 0. So as n goes to infinity, A2n plus 1 will also go to 0 because it is a subsequence of the sequence of ANs. So this is 0. So this would then imply that S equal to S prime. But since S is equal to S prime, this would then imply that the sequence of partial sums Sn, if I look at, this converges to S, which is same as equal to S prime. Okay. This is a simple fact about sequences which we have used earlier also, that if you have a sequence xn, look at its even subsequence, look at its odd subsequence. If the even subsequence and the odd subsequence has the same limit, then the whole sequence also has the same limit. In particular, it converges. By that observation now, the sequence of partial sums of the alternating series Sn converges to a number S. This implies that the whole series converges. Now I am going to tell you about another test, this time without proof, but it comes very handy, and in many practical situations you have to use that test. It is called the Dirichlet test. Okay. So suppose An and Bn are two sequences. If number 1, that summation n from 1 to m An, which I call Sm, is bounded, that means the partial sums of An is a bounded set. Number 2, Bn is decreasing and Bn converges to 0, then summation over n An Bn converges. This is called Dirichlet test. Let's elaborate a bit on condition 1. What we mean is, you look at S1, which is just A1, then you look at S2, which is A1 plus A2, then you look at S3, that is A1 plus A2 plus A3, and so on, so that Sn equals to A1 plus A2 up to An. Look at these numbers. Then these partial sums are bounded. It means there exists some m bigger than 0 such that modulus of Sn is less or equals to m for all n. This is what we mean by saying that Sm is bounded. That means there exists a number capital M such that in the modulus the partial sums of An are less than or equal to that number m. Okay? If that happens and Bn's are decreasing and Bn going to 0, then the series summation over n An Bn converges. This is called Dirichlet test. So let us just illustrate it by the following example. Look at the following series. Summation n from 1 to infinity, cosine of n theta divided by n, where theta is a fixed number and theta is not equal to 0. Notice that if theta equals to 0, then this series does not converge, because then cosine of n theta is 1 and summation 1 by n does not converge. But if theta is non-zero, then we are going to prove that this series converges. So what we do is we want to apply Dirichlet test here. So I put An equal to cosine n theta and Bn equals to 1 by n. Okay. Now Bn's are decreasing and decreasing to 0, that is clear. So this is decreasing and Bn goes to 0. Now all I need to prove is that summation n from 1 to m cosine n theta, if I look at the mod, it is less or equal to some number capital M for all m. So essentially now I am bothered about this kind of a finite sum, that is cosine theta plus cosine 2 theta plus up to cosine m theta. I want to show that this is less or equals to capital M. What I do is I view cosine theta as real part of a complex number, and that is a very well known complex number, all of us know it. If I look at e to the power I theta, this is cosine theta plus I sine theta, and we also know by de Moivre's formula that e to the power I n theta is cosine n theta plus I sine n theta. Okay. Now, since it is always true that real part of a complex number in the modulus is always less than or equal to the modulus of the complex number. Okay. The real part of a complex number in the modulus is always less than or equal to the modulus of the complex number. So this then implies that modulus of cos theta plus cos 2 theta plus up to cosine m theta is certainly less than or equals to modulus of e to the power I theta plus e to the power twice I theta plus up to e to the power I m theta. Now notice that the right hand side sum I can actually calculate because it is a geometric series with common ratio e to the power I theta. So I am going to use that e to the power I theta plus e to the power twice I theta plus up to e to the power I m theta, that I can write as e to the power I theta into 1 plus e to the power I theta e to the power I m minus 1 theta, which then by a well known formula of GP series is 1 minus okay. Now this implies then that modulus of e to the power I theta plus up to e to the power I m theta is modulus of e to the power I theta into 1 minus by the previous formula. Now since modulus of e to the power I theta or e to the power I n theta is always 1, what I get is that this is equals less or equals to, using the triangle inequality, 2 divided by modulus 1 minus e to the power I theta. The point is now things are independent of m. This is true for all m. This then implies that modulus of cosine theta plus cosine 2 theta plus cosine m theta is less or equals to this is well defined as theta is not equal to 0. Okay, and hence the Dirichlet test applies. I go back to the previous step. This m I have actually found out. This m turns out to be 2 divided by modulus of 1 minus e to the power I theta. It depends on theta it seems, but that is okay. It should not depend on the little m's, which it does not. So the partial sums of an's are bounded, bn's are decreasing and going to 0. This then implies by Dirichlet's test that the series converges. This is all we had to cover in the infinite series. In the next lecture, we are going to talk about something called power series.